Okay, in the homework, you're given a system whose input-output relationship is a complex function of the real variable omega. So to say that it's a complex function is to say that h1 of omega has a magnitude and an angle. And both the magnitude and the angle vary as a function of omega. Okay, so what we said in class is if I have my typical type of input that I would have to most types of circuits and systems that we have in ECE, I would have something of the form a cosine omega t plus phi. Okay, now that can be represented, of course, as the real part of a e to the j phi times e to the j omega t. Okay, so what we've said is that, okay, we can just think of our signal as a complex exponential and at the end take the real part. Okay, so if x of t was a complex exponential, so in other words, if I just had a complex exponential, my output is basically going to be whatever h1 of omega is. So h1 of omega times that input. In other words, this guy is h1 of omega times x of t, right? And my h1 of omega is given by this guy. Now this only happens for this special type of input, e to the j omega t. It doesn't happen for all inputs. Now that's not all that important for us, but you'll learn more about that in signals and systems. For us right now, we want to understand how to deal with this magnitude of h1 of omega and angle of h1 of omega. Okay? Now, remembering all of this basically says that my output, my final output, y of t, should just be the real part of h1 of omega times a e to the j omega t, like so. So let's look at a specific example. Okay, so here my input is 2 cosine 100t plus 30 degrees. So that says that I'm putting in an input signal which has omega equal to 100 or has a period t equal to 2 pi over 100. Okay, and so I can express this guy as the real part of 2 e to the j 30 degrees times e to the j 100t. Okay, so if I express my input that way, basically I'm going to forget the whole real part thing for now and just take this dynamic phasor, think of it as the input to my system, and then figure out what y of t is. Now in this case, my h1 is given by this complex function right here. Okay, complex function again, meaning that h1 of omega has a magnitude and an angle. Okay, so our goal is to figure out what is y of t. All right, so if that's the case, what we've said is if I have going into my system 2 e to the j 30 degrees times e to the j 100t, my output should basically be y of t equal to h1, well, y of t is the real part of 2 e to the j 30 degrees times h of 100, right? H of 100, because omega is equal to 100, times e to the j 100t. Wrote that guy too close to the edge there. Let's see. So h of 100 times e to the j 100t, like that. Okay? All right, so our goal here to be able to solve this problem is to be able to figure out what is this h of 100. Okay? So in this case, all right, following through with this example, right? Here was my input. Here's my h1 of 100. Now the thing to remember here, let's write this guy out. h1 of 100. All right, reminding ourselves that h1 of omega is equal to 1 over j omega times 10 to the minus 4 plus 1. I need to remember that at that particular frequency, I have 1 over j times 100, so that's 10 squared, times 10 to the minus 4 plus 1, or 1 over j times 10 to the minus 2 plus 1. Okay? So if I look carefully at that guy, that's basically, in my mind, one complex number, a, divided by another complex number. Okay? So I can say that the magnitude of h1 is equal to the magnitude of a divided by the magnitude of b. And I can say that the angle of h1 of omega is equal to the angle of a minus the angle of b. Okay? So here, down at the bottom, I calculate those two things. So the magnitude of h1 at 100, right, is the magnitude of the top minus the magnitude of the bottom. All right. So here it is. Okay, here's the magnitude. So the magnitude of the top is just 1. The magnitude of the bottom is the square root of the imaginary part squared plus the real part squared. Okay. Now for the angle of this thing, I evaluate the angle of h1 at 100. All right, so that's the angle of the top. So if I look at the top is the number 1. So it has an angle 0. Then I subtract the angle of the bottom. So if the bottom is j times 100 times 10 to the minus 4 plus 1, it's minus the angle of 1 plus j times 10 to the minus 2. Now, I just wrote that as angle. Of course, I got to express that as the arctan. So I say minus arctan of 10 to the minus 2 divided by 1. So imaginary part over real part. All right, now to evaluate that, what I do is I go into MATLAB to evaluate it specifically. All right, so within MATLAB, here's the code that I write. So I say, let's let omega equal to 100. So I just have a pure number for omega. What's the magnitude of h? Well, in this case, I just do this expression right here. Now notice I don't have any of these dot multiplies, okay, or dot powers, or dot divides. The reason I don't is because omega is a single number. I'm operating only on numbers here. I'm not operating on arrays or vectors. Okay, so I don't need those element-wise operations. For the angle of h, notice what I did here. A couple of things. I just said minus the angle of the complex number. I could have said minus arctan of, so in MATLAB I don't express it that way, right? I'd say minus, in MATLAB I say minus atan of omega times 10 to the minus 4, like that. Okay. Now, angle is basically an expression that deals with things in the second and third quadrant, so it makes the operations a little bit easier for me. Now, MATLAB defaults everything into radians, and so I have there a unit conversion that goes from radians to degrees. Remember, to go from radians to degrees, I have 180 divided by pi. And if I was going from degrees to radians, I would have pi over 180. Okay. So what I do is I put these things into this script, complex function examples. I run that and I get these results. Okay. So it tells me that the magnitude is 1. So it says that h1 of omega, so h1, specifically h1 at omega equal to 100 is 1. And the angle the angle of that guy is equal to negative 0.5729 degrees. Okay, so how do I express the ultimate output? Well, remember that the output is the real part of the input. So here, oops, here we go. Here is my input, okay? So it's the real part of the input times h1 of 100. Now, in this next line here, I've substituted in, here's the magnitude of h1, here's that e to the j angle of h1. So I take the real part of that. The real part of that would be a cosine, so I say 2 times 1 is 2, times cosine of, I got to combine all those e to the j things. So cosine 100t plus 30 degrees minus 0.5729 degrees. Okay? Now what I want to do quickly is I want to look at what that looks like in MATLAB. Okay? So here's what I did. I have a piece of code that I wrote, all right, that allows me to plot the different outputs. So specifically, I'm going to say, and it starts here on line 22 of my code, I defined a period. So in this case, my period is 2 pi over 20,000. All right, since my input had a frequency of 100 radians per second, I'm going to change that to 100. So this is the period I've defined. All right, so I'll call this the period. And then here, this is my delta t, this is my step. What I'm saying is I want 1,000 points in a period. So my step is basically t divided by 1,000. That's going to give me effectively 1,001 points in a period, but it's close enough. And I'm going to do this from 0 in steps of delta t up to 2 times t, which means I'm going to plot this over 2 periods. Now notice what I've expressed here. This is my h. So let's go put these two things next to each other here. Okay. So in this particular case, what I said was my magnitude of h was 1. So I'm going to make my magnitude 1 times the exponential of minus j times the angle that I got was negative 0.5729. Okay, so notice what I've done is I've written h here as evaluated at omega equal to 100 radians per second. Now, notice, as I said, MATLAB defines everything in radians. So what have I done? I put in 0.5729 degrees, but I have to multiply by pi over 180 to convert that into radians. All right, now what I've done is here I've written the input x, right? So 2 cosine times 2 pi over t. So 2 pi over t is the frequency in radians per second. And then I add the 30 degrees, and I had to convert that 30 degrees into radians, so I have that pi over 180. Now what I have here is two different ways of looking at that output. So what I've done is I have y1, where I've said basically that I have exactly what I've said it's supposed to be here, right? So I've written this guy two ways. I'm going to zoom this out a little bit. All right, so I've written this guy two ways. The first way is I've said the output is going to be 2 times the magnitude of h. Now notice the way I've written this here. I said abs of h. Abs is the magnitude, and I can check that real quick. So let's type help abs in my command window. So abs is the absolute value of the elements of x. When x is complex, abs of x is the complex modulus or magnitude of the elements of x. So what I've done by taking the absolute value of h is I'm going to get the magnitude. Now I multiply that by cosine 2 pi t plus, now notice this, here's that 30 degrees, all right, because that's the 30-degree shift that we have in the input. And then I add to that the angle of h, okay? Now notice the angle of h, I don't do anything funny with that. I don't change the units of that because the angle function will always output in radians. And my cosine always expects everything to be in radians. y2 here, okay, I do just the same sort of thing, but let's compare. For y2, what I have is the real part of h times the magnitude of the input times exponential j times omega t plus the 30 degrees. And notice on the 30 degrees, I have that unit conversion again. So basically what I'm doing in y2 is I'm essentially putting in this guy here, right? And what I'm doing is taking the real part of it. If my math is correct, and if I plot y1 and y2, they better sit on top of each other. Now down here, that's exactly what I did, right? I'm plotting three things together. So whenever I have these pairs in the plot function, so t comma x, t is my x coordinate, or my x-axis variable, x is my y-axis variable, t is my next x-axis variable, then I plot y1 and y2. So what this is saying is plot x, y1, and y2 all together at the same points t. Now if I want to just run that piece of code, I basically hover over this and evaluate selection, and there I get it. All right, what I see is that pretty much all three of those things sit on top of each other, which they kind of should for the most part, because you know, I only have a negative 0.5729 degree phase shift, and the amplitude didn't change at all. Okay, so let's try another case here. Let's say instead that I had a different input. Let's say I had x of t equal to 2 cosine. Let's say I had 20,000 t plus 30 degrees. Okay, so in that case, I have the real part of 2 e to the j 30 degrees. So that part hasn't changed, except I have 20,000 now as the frequency. That means that y of t is the real part of h1 of 20,000. So I evaluate that complex function now at a different frequency times 2, or write the 2 out in front, times e to the j 30 degrees times e to the j to 20,000 t. Okay? All right, now what I could do is I could go back and I could evaluate directly at h1. The other thing I can do is basically use the graph that I've asked you guys to create in the homework assignment. Okay? So in this case, here's the code that I use to generate the graph of the magnitude and the angle versus frequency. So what I'm going to do is I'm going to evaluate those guys real quick. So I highlight that, and I do, so I highlight it, and then I do evaluate selection, and there it is. Okay. So what I want to do is I want to evaluate the magnitude and the angle at 20,000. So I see that my x-axis here, I have 2 times 10 to the 4th. Right, so notice that this guy is in units. It's a little deceptive. It looks like this is 2, but I have to pay attention to the fact that all of the numbers here on the x-axis are multiplied by 10 to the 4th. Now what I'm going to do is I'm going to hover over the graph here for a second, and I see I got a bunch of tools that pop up. One of the tools is this thing here called a data tip. So I'm going to click the data tip. In other words, I want it to be blue. And I'm going to hover over right around 20,000. So I'm not quite at 20,000. I'm at apparently 20,510. So I can use my left arrow now to push backwards to 20,000. So I'm pushing slowly back there. I can use my mouse to try to move a little bit faster. Get it close. There we go. And then go to 20,000. Get ever so close. Ever so close. Ever so close. There we go. All right. So it looks like what this is saying is that the x-coordinate of 20,000, my y-coordinate is 0.4472. So what that says is the magnitude of H1 of 20,000 is 0.4472. Now I got to figure out the angle at that point. So I go down here, hover over again, left click with my mouse, and I try to move that guy a little bit closer. And then I'm going to right click with the arrow, and it looks like the angle is negative 63.43. So the angle of H1 of 20,000 is equal to negative 63.43 degrees. So what does that mean? That means that y of t is the real part of 0.4472 times the magnitude of the input times e to the j angle of the input, which is 30 degrees, times e to the j angle of h, which is minus 63.43 degrees, times e to the j 20,000 t, okay? Or 2 times 0.4472 cosine of 20,000 t plus 30 degrees minus 63.43 degrees, like so, okay? So in this case, go to my MATLAB. So again, at line 22, I'm going to change this guy because my period's different now. So I change my period to 20,000. Okay. Keep everything the same. Now, I'm going to change my h though, because my h is different, right? My h has a magnitude of 0.4472 and an angle of 63.43 degrees. Okay. Nothing else changes about any of this stuff. Okay. So I'm going to highlight, right click, and then evaluate selection. And boom, everything kind of updates. The blue is the input. See that it's got an amplitude of 2. And then over here, there's actually two things sitting on top of each other. One of them is the cosine, and the other one is the real part of the exponential. All right, so if you follow this approach and you follow this code, I'll post this code as well on Canvas, you guys should be able to figure out what's going on. Hope that helps.